Question 14 from the 2019 Advanced Higher Physics Examination from the SQA. A point charge of plus 1.3 times 10 to minus 14 coulombs is placed 48 millimeters from a point P. Show that the electrical potential at P due to this charge is 2.4 times 10 to minus 3 volts. Well, here we have the situation here. We have the charge 1.3 times 10 to minus 14 coulombs, and we have point P, which is 48 times 10 to minus 3 meters away. That's when we change 48 millimeters into meters. So what is the formula for the potential at the point P? Well, if we bring down our formula sheet, you can see that we have the following. The potential is V and is equal to Q over 4 pi epsilon naught R. So that's the third equation down there, which we have shown ringed. So that's the equation which we're going to use. So if we put down our equation now, then we have got V is going to equal to the charge Q divided by 4 pi epsilon naught, and R standing for the distance which the charge is away from the point. So we'll put by our formula sheet, and that's us got our particular equation. So I can move the equation over here and ready to start it off. Now we know the value of Q is going to be 1.3 times 10 to minus 4. We know 4 and pi, and we know R, the radius, but we have to find this epsilon naught. So we've got to bring down our data sheet here like that and scan the data sheet to see if we can find epsilon naught, which is called the permittivity of free space. And there it is there, highlighted, epsilon naught, which equals 8.85 times 10 to the minus 12. That's it, highlighted in. You'll find that in your data sheet at the front of your exam. So we'll put our data sheet by, and now we'll go ahead with the actual working out of the equation. Oh, it's quite simple then. We have Q is going to be 1.3 times 10 to minus 14 divided by, we'll put this in a bracket, 4 times pi times 8.85, we looked that up, 8.85 times 10 to minus 12 multiplied by R, which is going to be 48 times 10 to minus 3 of a meter. Remember, we put that into meters rather than millimeters. And if you do that successfully in your calculator, you'll get 2.44 times 10 to the minus 3, and remember it's a potential, so it's got to be measured in volts. Of course, you can put it down to two significant figures, and our final answer will be 2.4 times 10 to minus 3 volts, and that's our answer. Question 14a, part 2. A second point charge of minus 1.3 times 10 to the minus 14 coulombs is now placed 52 millimeters from P. And we can see that in the diagram. And for 3 marks, we have to determine the electrical potential at P due to both charges. Well, we know this important fact. The electrical potential V is a scalar quantity. So we just add the quantity together at a point to get the overall potential. And we've got to take into consideration the signs of the potential. Now, in the previous part of the question, we found out that the potential at point P due to the plus charge was 2.4 times 10 to minus 3 volts. So all we have to do is work out the second combination, and that's V minus, we'll call it, and that's due to the negative charge. And that's going to be given by Q, it's the value of the charge, over 4 pi epsilon naught R. So we put in the numbers in. Q is going to be minus 1.3 times 10 to the minus 14. And we're going to divide that by the bracket in the bottom, 4 times pi times epsilon naught, which is 8.85, multiplied by 10 to minus 12, and then multiply it by the distance at point P is away from that charge, which is 52 millimeters, which we can write down as 52 times 10 to minus 3 of a meter. So we do that calculation, we're going to end up with a value of minus 2.25 times 10 to the minus 3 volts. And that's going to be the combination, the potential, electric potential due to the contribution of the negative charge. So to find the overall potential at that point P is going to be V plus V minus. So it's going to be equal to 2.24 times 10 to the minus 3 volts, and because it's minus this time, take away 2.25 times 10 to minus 3 volts. And that's going to give us an answer of the value of 0.15 sorry, times 10 to the minus 3 volts. And that's your answer. We can put that into standard form by saying it's 1.5 times 10 to the minus 4 volts. But a key point here is just add the contributions of the charges together at point P. Question 14 continued part B. Some virtual reality headsets detect changes in electrical potential caused by movement of charge within the human eye. The human eye can be modelled as 2-point charges. In this model, there's a positive charge near the front of the eye, the iris, and a negative charge near the back of the eye, the retina. And you can see the diagram there shown in figure 14b. Now, when the eye looks from side to side, the positive charge moves while the negative charge remains in a fixed position. An electrode in contact with the head can measure the electrical potential at that point due to these charges. So for 2 marks, we're asked to state what happens to the electrical potential at the electrode as the iris moves towards the electrode. So here we have this situation here. That's the original position. You can see we've made Ri being the distance from the iris to the electrode, and Rr being the distance from the negative charge at the retina to the electrode. So the potential at P is just really the sum of the two potentials, the one from the iris charge and the one from the retina charge. And we can write that out in full as like that, knowing that the charge in the retina is negative. So we'll get Q over 4 pi epsilon naught Ri, take away Q over 4 pi epsilon naught Rr. Now when the eye moves like that towards the electrode, you can see that Ri gets smaller. So if we concentrate on the Q over 4 pi epsilon naught Ri, if Ri gets smaller, then this quantity Q over 4 pi epsilon naught Ri is going to increase. Now bearing in mind the second part of the equation, which I've shown ringed there, stays the same, it means that the first part of this equation is going to increase. And if the first part of the equation is going to increase because Ri is getting smaller, it's on the denominator, then overall the potential at point P will increase as well.